Hey guys, welcome back to AlgoYogi. We are now doing graph series. Our next problem in the list is clone graph. Let's go to LeetCode. So given a reference of a node in a connected undirected graph, return a deep copy, which is also a clone of the graph. Now each node, basically they have given the definition of the node that's going to have a value and this list of neighbors. So it's like adjacency list. Now these are like basically they have given us how we're going to clone it. So this is the first example, and you cannot reuse those available nodes. You cannot mess up basically the order of the graph. You cannot switch the nodes. Your copy has to look exactly like your original graph, but then you have to clone these edges, and you have to clone basically the vertex as well. So these kind of problems we have seen before. They mostly are asked on non-linear data structure. We have done similar problem on linked list, and then we have also done same problem on cloning a tree data structure. So usually interviewers ask this problem so they can test. It's usually on the easier side of these interview problems, where the interviewer is kind of test that are you able to iterate through these traverse through these non-linear data structure at the same time, using that recursive method and that call to basically link these cloned copy of these vertex or nodes, whatever you guys want to call it, and also return back safely and return basically this copy. Okay, let's see how we are going to do it right here. So this is the graph that we have. Now this will be given to us in a way where we are given these nodes, their values and their neighbors. So let's say if this is the node, 1 is the node, then its neighbor is going to be basically these values, which is 2, that's 1, and then 4. So these are its neighbors, and this is the node. So then there is one more node, and then 3, and then 4. All right, so this is going to be like this. Now I have like just written it so that it's easy to understand, but like in reality what's really must have happened is like these nodes, while these nodes we're creating this list, but then it's also these vertices, they're actually connected, and one neighbor, like if I'm your neighbor, then you are also my neighbor. So that's what I'm trying to say, like that's how they are connected. So 2's neighbor is definitely going to include 4 as 2's neighbor is going to include 1 as well. So 1 and then 3, and same 3 is going to have 2 and 4, and then 4 is going to have 1 and 3. Okay, so this is the graph that's given to us. Now how are we going to create the copy? Well, we're going to use recursion, and specifically DFS, which is depth first search. And while we are basically traversing through our graph, for each of the node we will create a copy of that node, and then at the same time we will create copy of its neighbors, and then put them into the copies neighbors. So but here one more thing that we want to do is we don't want to create like too many copies of the same node. So I will use a HashMap to basically link the copy of these nodes, and to have like value as the copy, the new node that we are going to create. So I will have a HashMap. Let me just create this HashMap right here. And oh my god, that was like the weirdest rectangle I've ever drawn. So I'm going to create this, and then it's going to have map. This map is going to have a old node and copy. Okay, So what I'm gonna do, I'm gonna basically have my depth first search or traversal on our graph. Basically we will be given a node to basically begin our DFS to start the traversal. So let's say in this case we are given 1. First thing I'll be doing is checking if this is present in my hash map. No, it's not. So what I'll do is I'll add it to my hash map, and the reason I'm using hash map is just so that I can store these copies of these copy node that I'm creating of the old node at the same time, so that later I can access that copy immediately if that old node was neighbor of some other node. So I create that copy. Now what I do, I'm gonna start visiting the neighbors of 1. So these are the neighbors of 1. These are the neighbors of 1. First neighbor is 2, so I'm gonna visit 2. Is 2 present in my hash map? No, it's not. So I will add it to hash map, create the copy, which is going to have the same value. Now so what I'll do is, like when I'm creating this, at the same time what I'll be doing is I will attach that to the neighbor of this clones list, clone graphs nodes list, the neighbor list. So I'll add that right here as well. Now I'll be visiting 2. So I'm not done visiting one's neighbor, all the neighbors, but since it's a DFS and I have already started traversing 2, so what I'll be doing, I will now visit all the neighbors of 2. So now this is my list that I'll be visiting. This is the neighbor, these all are the neighbors of node 2. So I'm gonna start visiting 2, but I see that this 1 is the neighbor of 2. It's already present in my hash map. So what I'll do is I'll attach that copy or this. I think most likely what will happen is like there is an edge going from 1 to 2. So 2 is in 1's neighbor, but then I'm adding 1 also, 1 as a copy clone or whatever you want to call it, as a node into 2's neighbors. So I will add that. Okay, I will add that. Now there is another node, 3rd. So I'm only visiting them when I see that those nodes are not present in my hash map. So I see 3 now. 3 is the node that I'll be visiting. It's not present in my hash map, so I'll create a copy and add that to my hash map. So 3 is added now. Now 3 is going to be the neighbor of 2. Since it's the neighbor of 2 in the old graph, I'll add that to 2's neighbor. So here 3 will take we will add 3 to 2's neighbor. Now next thing, since 3 was not present in our hash map, I'm gonna start traversing 3. So 3's neighbor, first neighbor is 2. Since 3 I've already created the copy of 3. Now I'm only visiting its neighbors. So I see 2 is in 3's neighboring list. So I'll check if this is 2 is present in my hash map. Yes, it is. So I'll add that to its 3's neighbor list. So this will be added, and I'm gonna just draw these double directed edges so that we can like keep a track that 1 is pointing to 2. That means 2 is in 1's neighbor list, and then 1 is also in 2's neighbors list. Now what are the nodes of 3? 2 is visited. How about 4? 4 is not present in my hash map, so I'll add 4 to my hash map, and then also have the value 4's clone, the node's clone attached to it. So I will have 4 created. Now since 4 is neighbor of 3, so I will have an edge going outward from 3 to 4. So that's like out degree or in degree for 4. Then I'm gonna check since 4 was not present in my hash map and I just added it, so I'm gonna start traversing 4 now. So this is 4. I'm traversing its neighbors now. Now you'll see that 1 and 3, they're both present in our hash map. So in this case I'll just directly get the copy and add that to 4's neighbor. So 4's neighbor 3, and 4's neighbor is 1, and then 1's neighbor is also 4, and that will be added once you return back. So first we'll be done traversing 4, and then 3, and then 2. So you are basically our control is being returned from this recursive DFS function from here to 3 to 2, and 2 to 1, and that's how you basically return this graph. We're basically returning this node where we started from, but like now it's a cloned node of the cloned graph. So that will be basically the time complexity is going to be big of v plus e, where v is the number of vertices and e is the number of edges. Okay, so let's write down the code, and space complexity is going to be also same, because we are at the end like returning this copy, and we are maintaining that reference in the memory, but at the same time we are using HashMap. So you can say like this HashMap is going to store all the vertices, so but edges is like what we are returning these neighbors. Okay, so let's write down our code. Okay, as I said, we're gonna have a hash map. Let's call it old to new nodes. So this is going to be a graph. Now what I want to do is I'll have my DFS function. So this DFS function will be taking a node. This DFS function will be taking a node. This node, that's the node that's given to us right here, and that's where we will start traversing, right? So let's say if this node in my old to new nodes graph, hash map, or instead of nodes I'm gonna call it map, so that it makes more sense. So if this is present here, then I want to just return that copy that's already stored in my map. So I will return that map value. So this is a node that we are returning whose copy is already present in my old to new map. What if it is not? Then I'll create the copy. So I'll create the copy. How do you create a copy? We have been given this class node. So in the node we will basically add the value, right? We will add the value, and what is the value? Value will be the node.val. So that's the copy. But what I want to do is I want to visit neighbors of this particular node. How do you access the neighbors? We'll have node.neighbors. So I want to visit all the neighbors of this, and then I want to append those to basically whatever those neighbors are, their copy to basically the copy's neighbor. So copy is what I'll be returning in the end. So this is what I'll be returning in the end, copy. But before I return it, I want to add recursively all the neighbors of this original node, this node from our original graph, to the copy, basically the clone. So copy dot neighbors, that is basically a list dot append. And what am I appending? I am appending DFS on basically these neighbors. So this neighbor, basically not neighbors, neighbor, and it will be called like on all the neighbors, because this is a for loop. It will be calling on all the neighbors. Then I'll be appending all those neighbors to this copy, and finally at the end once we are done visiting, since it's a connected graph, it will keep making all these recursive calls to all on all of these vertices and whatever neighbors they are connected with. And then finally, once it's done adding all the neighbors to their neighbors, all the nodes and the neighbors to each other, and then it will return the copy. Finally, we can just return our DFS function, but on the main node. So that is it. I think that will be all. Let's try to test this on our examples, basically test cases. We forgot to add these new copies that we were creating to our basically hash map. We are trying to access it, but we will never be able to access it if we don't add it. So it's going to be node is going to have the value basically copy. We're going to have the value copy. Okay, so we're just creating the copy. Copy will have its own reference once we enter all of these. So we can have it right here, we can have it in the bottom, wherever you want it. It wouldn't change anything. One more thing is what if the node is none in the beginning? So we can have this right here. If node is none, then return none. Okay, so I think now we're all good. Let's test it out. And yeah, let's submit it. Awesome, that's a pretty efficient solution. Let's write down the non-complexity, which is going to be big of v plus e. So we were visiting all the vertices and all the edges, and then space complexity is going to be big of v, or you can say v and e, because since we are kind of when you're creating this new copy or clone, then we are utilizing same space that our original graph used, which is v plus e. Okay, so let's go back to AlgoYogi, mark this problem solved. See you guys in the next problem.